Hello everybody, welcome back to the Arithmetic Zone. Today we're going to be doing an AP Physics C problem. The 2022 FRQ Set 1, question number 2. Let's get right into this, guys. Alright, so this is our question. Let's read it. A block of mass M starts from rest at point A, so it starts from here, and travels with negligible friction through the loop onto a horizontal surface where the block makes contact with a spring of spring constant K is equal to mg over 2r. All of the motion of the spring is in the horizontal direction. Point C is the highest point of the loop, and point B is the rightmost point of the loop. Express all your algebraic answers in terms of m, h, r, and physical constants as appropriate. So first, let's start writing down some givens. So we're giving that our mass is equal to m, our radius is equal to capital R. It says right here it starts from rest, so our initial velocity is 0 meters per second. Negligible friction, so for all intents and purposes, friction is 0 newtons. We're given K right here, and it's all horizontal movement, no vertical movement. We're also told that our heights at the specific points. At A, our height's equal to h. At B is the rightmost point, meaning height is equal to the radius, which is r, and C is the highest point, which means it's equal to diameter, or just 2 times radius, 2r. Okay, and here we just have our givens and our heights written side by side, and let's move on to the first part of this question. Alright, so here's part A. On the dot below, which represents the block, draw an arrow that represents the direction of the acceleration of the block at point B in the figure above. The arrow must start on and point away from the dot. So they're saying, what's the acceleration here at point B? So let's get into it. So here we have point B drawn. This is a point B. So towards the Earth, there's acceleration due to gravity, or g. And then since this is in a loop, there's centripetal acceleration happening, which is pointed towards the center of the circle, or in this specific case, to the left, technically. But they want the net acceleration, which is the combination of these two. So that would be right here down the middle. Just like this. That is our net acceleration of the object at point B. Now they want justification as the second part of it. So the centripetal acceleration points towards the center of the circle, while gravitational acceleration points towards the Earth. This means the net acceleration is directed between the two directions, and also it must be longer than them. But you're not drawing the components, so the size really does not matter. It's just the direction that matters. It has to be in between here and here. Alright, now here's part B, part 1. To derive an expression for the speed, v, of the block at point B. So let's start off simple. So our total mechanical energy, let's make that ET. And as we said before, there's no friction, so that means the total energy is conserved. This value doesn't change. Since total energy is conserved, our total energy is equal to kinetic energy plus potential energy, and that's gravitational potential energy. Unless it's at the end where the spring is, but that's, for all intents and purposes, that doesn't matter yet. So as we have here, our kinetic energy at point A plus our potential energy at point A is equal to our total energy, which must then therefore be equal to our kinetic energy at point B plus our potential energy at point B. So let's come back here and I'll show you. So our total energy here is the same as our total energy here. Kinetic and potential here is equal to kinetic and potential here. But that doesn't mean the kinetic energies are the same or potential energies are the same. They just add up to the same value. So here, we're going to expand out our formulas. Kinetic energy is equal to 1/2 mass times velocity squared. The potential energy is equal to mass times gravity times height. So, and here we just have it expanded outwards. The A for VA, that's a velocity at point A. HA, height at point A. VB, of course, velocity at point B. HB, height at point B. So here we have, as we said before, in our givens, our initial velocity is 0 meters per second. That's our velocity at point A. So we'll come here, so that means our kinetic energy at point A is 0 joules. So that just cancels out. So mass times gravity times height, because our height at A is just h, is equal to 1/2 m velocity at b squared plus mg capital R for our radius, which is our height. Our m's cancel out, so now we're left with gh is equal to 1/2 vb squared plus gr. Subtract over this gr. Now we have this equation here. Then multiply it all by 2. And then square root it. And we're left with our final equation here. Our velocity at point B is equal to the square root of 2g times h minus r in parentheses. Okay. Now let's move on to number 2 for letter B. And I want us to derive an expression for the magnitude of the net force F on the block at point B. So, as we said in part A, we know we have a centripetal acceleration and a centripetal force. I'm sorry, not a gravitational acceleration. So we have an acceleration in these directions, we must also have a force in these directions. So we have a gravitational force downwards and a centripetal force towards the center of the circle. Now coming back here, if we draw a right triangle, so it's not 100% straight, but it's meant to be. And we use Pythagorean's theorem. A squared plus b squared is equal to c squared. Our hypotenuse would be F net, and our legs would be the force of gravity and the centripetal force. So here's our equation. Here we simplify F net is equal to the square root of centripetal force squared plus gravitational force squared. The force of gravity is equal to mg, and centripetal force is equal to mv squared over r. As we established, velocity at this point is our velocity at b, which is the square root of 2g times h minus r, all in parentheses, just like this. Now, we plug in our values for fc. M times our velocity, since it's in the square root, just squaring it takes it out of the square root. So that leaves us with 2mg times h minus r, all divided by r. And now we plug it back into our fnet formula. Fnet is equal to fc, right here, squared, plus fg, here, squared. And it's the square root of all that. And see, it's pretty simple. Now let's go on to C, my friends. In terms of r, being the radius, derive an expression for the minimum height, which is h min, necessary for the block to maintain contact with the track through point C. So a h minimum, that means that the the normal force, which is causing our centripetal force, is 0 newtons. And that means our centripetal force is only caused by gravity in this scenario. So, using that knowledge, we're going to return back to our mechanical energy equation we had earlier. Total mechanical energy is equal to Ka plus Ua, and now we're using the point C, so Kc plus Uc. As we established before, kinetic energy at point A, 0 joules. And here, H is going to be substituted for H min for our height at A. So our potential energy at A is mg h min. Now right here, we plug in our values we substitute in the equations for kinetic energy at C and potential energy at C, make it equal to potential energy at A, and we can cancel out our M's. We start to simplify, bring over that 2R, multiply by 2 here, and then square root it all, and here we have our velocity at point C. But that's not what we're asked to find, that's part of our way to solve this question. Now here, we're going to make an F-net equation. Our F-net at C is equal to the centripetal force, which is equal to the summation of F, which is Fn plus Fg. As we said earlier, Fn is 0, and Fg is, of course, mg. Since the centripetal force is equal to mv squared over r. Our radius is equal to capital R, and our v is equal to velocity at C. Now mg is equal to mvc squared over r. Cancel out the m's, and simplify to solve for vc, our velocity at point C. Now from here, we have velocity of C is equal to square root of rg, and velocity of C is equal to square root of 2g times h minimum minus 2r in parentheses. They're both equal to vc, the velocity at point C. So from here, what we can do is we can make them equal to each other and solve for h min. Here's what we're going to do. We're going to square both sides to get rid of the square root. Now rg is equal to 2g times h min minus 2r in parentheses divided by 2g. Well, for r over 2 is equal to h min minus 2r. Add over that 2r, and we get 5r over 2, or 2.5r, is equal to h minimum. Pretty straightforward. Alright, now we're at D. Oh, we'll get a little highlight here. It is determined that our height is 0.3 meters, and our radius is 0.1 meter. If the block is released from a height greater than that in part C, what's the maximum compression, x max, of the spring? So since it's a height greater, that means it's going to fully go through the loop, meaning there has to be some sort of compression. Now we're going to use our mechanical energy equation once more. Total mechanical energy is equal to Ka plus potential energy at A, but that's going to be equal to our potential energy in the spring at the end plus the kinetic energy. At the end, velocity is 0 meters per second, so our kinetic energy at that point is 0 joules. We already said kinetic energy at point A is 0 joules. So potential energy at point A is equal to potential energy in the spring. So potential energy, we said, is mgh, and potential energy in the spring is 1/2 kx squared. Now what we're going to do, make them equal to each other, plug in k, as we said was mg over 2r, and we're going to simplify it. As you can see here, the m and the g to cancel out, multiply over that 2r, leaving us 4hr is equal to x squared, then square root it, x is equal to 4hr all square rooted. Now here we're going to plug in our values. We said h was 0.3 meters, r was 0.1 meter. Plug it into our equation we had, 4 times 0.3 times 0.1, square root it all, and then x decompression is equal to 0.346 meters. Moving on to letter E, where we have our last part of this question. So a graph of the maximum compression of the spring as a function of height is shown below. The height, h min, is the height calculated in part C. So what they're saying is, this here, this is the height, this is compression. As you can see in this section 1, it doesn't exist, and that's actually part 1. Explain why section 1 appears as a horizontal line segment on the horizontal axis. So you may be saying, why is that? Well, if it doesn't reach that minimum height, it doesn't complete that loop. It'll go and it'll stop. Let's say there's our loop here, right? It'll go like this and it'll fall. It won't make it all the way until it reaches H minimum. So before it reaches H minimum, the object does not make it through the loop, so there cannot be any compression of the spring prior to that point. That's it for part 1. Let's go to part 2 now. Explain the reason for the shape of section 2 on the graph. If you notice here, section 2 isn't linear. It's like a square root kinda. So as we said earlier in part D, we've established this. X is equal to the square root of 4HR. And I brought that back here for you. That means that since radius is constant, right, and 4 is constant, the only variables that are changing is height and compression. So if you square it over, height is equal to the square root of compression. And this is the graph of that. So as we previously established, the height is proportional to the square of compression. This is what causes the shape that is seen in section 2 of the graph. Alright, now we're done with this question. Wasn't that hard, was it? Well, if you guys enjoyed, if you did, please leave a like and subscribe for more. This slide will be in the description, probably. And good luck with AP Physics, everyone. This was fun.